I'm here to talk about low energy design today. I also want to introduce Jim, who's over there waving his hands. He is the other half of Adapt Architects. That's our practice. We've both been practicing as architects for about 20 years now, and about three years ago we came together to form a practice, bringing our particular specialisms and experience together. So Jim is a qualified passive house designer. So really this is his talk, but I'm doing it because I'm more gobby than he is. So you'll have to listen to me again, I'm afraid. Anyway, so Jim is passive house designer. I'm a sort of tagger on. Anyway, I know lots about it. I also teach it as well at UE, so yeah. Okay, so you all know about this, the Paris Agreement, our commitment to, our legal commitment to limit global warming that we signed in 2015. You're probably also aware that there are lots of statistics out there about how polluting the built environment is. It varies depending on which talk I'm giving. This one says 49%, other ones say, anyway, a large proportion of the greenhouse gas emissions are linked to construction, and they still are in the UK and the built environment. So, you know, us in the construction sector are reacting rather slowly to this, not quickly enough. And there are multiple problems, multiple barriers to this, but our technical ability is there. We know how to make buildings extremely low energy. We know how to make them zero carbon. So we're going to talk about what we can do as designers and builders today. So we're going to talk about Passive House, which lots of people have heard of. So passive, it's about trying to reduce energy demand in buildings and make them as low energy as possible. It's not just about houses, although it's called Passive House. It started off as a standard that was looking at residential properties. It is now being used in all kinds of capacities, all kinds of buildings, from swimming pools. We had our first UK swimming pool, a leisure centre, Passive House certified last year. We have one of those pictures there is a housing scheme in Cambridge called Goldsmith Street. So that's 105 dwellings. So we're having sort of larger housing done in the Passive House standard. So it's about a really rigorous energy efficient design standard. That's what it is. It's a standard of construction and design. And the buildings are so well constructed and insulated and ventilated that they can retain heat from the sun and from the activities of their occupants, like breathing and cooking and showering and that kind of thing. And so they can require very little additional heating or cooling to keep them at a really nice temperature. So it's kind of acknowledged that they have quite high upfront costs and they can be more expensive to build than conventional construction, although the standards are creeping up with conventional construction now. They're becoming more similar to Passive House, so the cost differential is going down. Something that's very good about Passive House is that it is sort of very rigorous, and there's a really good quality assurance system built in, so it's a process. And in fact, it came out, the whole system came out of a frustration and acknowledgement that there was a really big performance gap between the design of low energy buildings and the actual reality of what you got at the end. So the Passive House standard has aimed to design that out through a process approach, a systemic process approach to achieving good quality. You'll see on there on the disadvantages that one of the disadvantages people sort of talk about is that there are constraints on the design aesthetic. So I wanted to show you these two photos here because, as you can see, you can get quite a lot of variety in design. So the one on the, that side, What's that? Right. That's a straw bale passive house building in Norfolk, which looks like any other straw bale cottage. And then you can get sort of, very shiny buildings. You can get, so there isn't actually, there's a lot of variety that you can get in the look of your housing there. Energy security. So that's something that's very important going forward. Reducing the energy demand of your home is a really good thing to do. We have, less energy security to look forward to in the future. So that's a really good, strong place to be if you have a reasonable level of self-sufficiency within your systems and are not using much anyway. And the Passive House standard can be compatible with net zero, which is where we're all trying to get to. Okay, so it was devised in Germany and came out of the kind of the fuel crisis in the 60s and 70s, and as I say, came out of this desire to get rid of the performance gap in low energy buildings. Okay, it's not the whole picture though. If we're trying to get to net zero, which is our aspiration, building a building that's very low energy is only part of the story. And you can see from this slide, we've got our operational energy. So that's what Passive House design system is trying to reduce the amount of energy that building uses to operate. So you can see that going along this timeline here. Also, we have to consider the embodied energy. So that's the energy it takes to build the building in the first place. And that's really quite a large proportion within things. Then we have moments of needing to replace and maintain throughout the building's life cycle. So there's more pink coming in here. Pink is the embodied energy, the energy embodied in the materials and the construction processes. And then we also have end of life carbon too. So just putting up a passive house building is only very much part of the picture of achieving net zero. It's also how you build and what you build, which is really important as well. So to get to that hallowed ground of net zero, we have to consider the whole picture. So this is kind of like a life cycle analysis diagram taken from the European standard EN 15978. So a whole life cycle analysis would look at the entire lot, right through to the circular economy considerations of the construction industry as well. Embodied carbon is looking at those A1 to A5 stages, which is about producing the materials and the construction. And the orange there again is the operational carbon and the operational water there. So they're just part of the processes. So it's just worth bearing that in mind, I think. So here we can see that at the moment about 80% of the annual carbon emissions associated with buildings is associated with operational carbon emissions. So if we manage to reduce those down, the load of the embodied carbon becomes more significant. So it's even more important while we're doing Passive House to be considering the embodied carbon as well as the load of the building in the end. And this is where we're aspiring to get to, obviously. So these are different scenarios with different sort of heat pumps and things coming in across there. Okay, so just a little tiny bit more on the embodied carbon. So before we start a project, we kind of really scale things back and sort of interrogate the brief. We do this with our clients, we do this in our practice, and we sort of follow this sort of mantra, if you like, that starts with build less. Is the building necessary? Does it need to be this size? Does it need to be this complex? We ask about whether there are existing materials we can use on site. We ask, can it be multifunctional? So we do a kind of efficiency review right at the beginning where we're considering actually can we build less than what we're building already, because that's our starting point. We also think about building light. So that is kind of really our structural considerations. How can we make this building as lightweight as possible? Heavy buildings require bigger foundations. That's more concrete in the earth. That's more embodied carbon. Can we avoid using steel? Steel has a large embodied energy load. It takes a lot of energy to make, and seeing as it's all made in China, it takes a lot of energy to transport here as well. Mostly made in China, not all. So we think about building light, and that's our conversations with our structural engineers in particular. Can we reduce these really long spans? You know, what are we doing that's really flamboyant here, that's bumping up the structural gymnastics of this building? Is it necessary? Maybe not. Is it desirable? Maybe. Is there another way we can do it? Those kind of considerations. We think about building wise. So are we putting materials that last a long time into this building? Are we reducing the amount of maintenance and rebuilding that's going to happen? You know, are we looking for locally sourced options, reducing our transport to site, that kind of thing? Are we designing the site, the project around the site topography so that we can avoid having to take too much fill off site? That's really energy intensive. So we're thinking about all that kind of thing. We're thinking about building low carbon. So again, using our low embodied carbon materials, and you know, particularly around structure and the envelope and that kind of thing. Looking to use natural materials, looking to use renewable materials as much as possible. Can we design things to be disassembled at the end of their life? So can we design things to be mechanically fixed rather than glued or welded? Then they can be reused and put back into the building stream more easily. So we're making all these considerations in our kind of design processes. We're thinking about the future, so we're thinking about those end-of-life scenarios for this building. If it's a residence, then is it flexible? Can it support people in that house right to the end of their life? You know, can it be adapted so that they can live in it in old age? If it's not a house, is it going to be flexible for uses in other ways, perhaps, if the use of the building becomes redundant? So thinking long term. Thinking also down to the macro, like are the materials we're using, can they be disassembled? If we're building out of brick, can we use a lime mortar rather than a cementitious mortar? Then we'd be able to take those bricks apart and reuse them very easily. So all these considerations. And the last one, build collaboratively. Well, that's really talking about involving everyone in those decision-making processes and talking to our clients and the design team and our consultants about to get everyone's expertise and opinion on the table. And also it's about making decisions at the right time. So making decisions early on in the process that are relevant. And if we need to use rules of thumb for data, we won't have exact data on things, to help us make decisions, and we can do that more generally at the beginning of the process and then be more targeted and specific going on. So these are some best practice targets that were put out by LETI, which stands for the Low Energy Transformation Initiative. Started out in London, probably almost a decade ago now. Amazing organisation, collective of young professionals who are really pushing the agenda, and it's now gone nationwide. Anyway, they sort of set out these best practice targets. One as a 40% reduction, which is kind of where we're aiming at the moment, and the second one as a whole life net zero target. So you can see there on the 40% reduction, they're saying we should be aiming for 500 kilograms of carbon dioxide equivalent per metre squared for our embodied carbon. They're putting a target there basically. And the energy use for the building should be optimised to balance, and we'll come on to that in a minute. But they're also talking about trying to use 30% reused materials in building, which is a real challenge, actually, in place of virgin materials or new materials, and 50% reusable. So thinking about how those materials can be reused at the end of their life if we're designing for disassembly. And then, of course, when you go to whole life net zero, everything just maxes out. It's either 100% or 0%. So, you know, that's how we do it. That's how we build net zero. But as I say, we're not there yet with that. So those are the sort of net zero targets there. And that at the bottom is the plan of work that architects work to. And that's just us thinking about at what stage in the process do we talk about these things, do we consider these things as we go through, and it's sort of being mindful of using those different stages to go into things in different detail. Okay, so we're talking about optimal energy balance, and we're talking about that today really, about how we do this side of the equation, which is the operational energy side of things. So this is about bringing down our demand to the absolute minimum. So building a house or a building that reduces the operational loads as little as possible. So to make this net zero, we need to balance our demands with our on-site renewables or off-site renewables, okay? And once we manage to do that, we're talking about a net zero scenario for the operational load. Okay, so we're not talking about carbon offsets at all. We're talking about things like roof-mounted PVs to provide that energy, battery systems to be able to store it. When we're moving towards electric cars, it's going to be interesting how people are using those in relation to their home energy and their batteries, and whether their electric car almost becomes a home battery. And so that, you know, there's a lot of thinking and development going on around that side of things. Okay, so good passive house design is based on trying to get as much free heat into our house as possible. So using solar gains, so that's the sun coming through the windows, basically, and landing in the house. And we can do that by making sure that we design our facades to respond to the orientation. So we're hoping that we've got a nice south-facing aspect that we can use by having bigger windows on that side to encourage the sun in. We're trying to simplify the building form. Complex building forms have got much more surface area, therefore more opportunity for air and heat to leave the building. More junctions. Junctions are always really complex in design because that's where you've got to stop. That's the most easiest path for heat to leave or problems to occur. A nice straight wall is very easy. So we try and simplify the building form. We put in large amounts of insulation to make the walls perform very well thermally. We make the walls airtight so that we're minimising leakage through the walls. We don't want to be having air escaping in an uncontrolled way. So we want to absolutely minimise, eradicate air leaking out of our building. That's why we call it airtight, which can be a bit alarming. And then we significantly reduce what we call thermal bridges. So thermal bridges are weak spots in the fabric where more heat can get out than we want. And as I say, that's usually in the junctions, either between materials or in the geometry of the building. We use very high performance glazing because glazing is traditionally a weak spot in the construction. So we're using triple glazing. And as I say, but we'll come on to it in a minute, we're designing that very carefully to do with the orientation and the size of the windows. We make sure that all our windows can open for natural purge ventilation so that our building can release heat when we need it to. The last thing we want is to end up having to put air conditioning on our home. So designing for cooling is very important. And then we ventilate our building in a very controlled way using what's called an MVHR, mechanical ventilation with heat recovery. So that's the way that we make sure the air is fresh in our building without losing any heat energy. And we do all this by using some software called the Passivhaus planning package, which is the mechanism by which we design this. So it's quite a technical design exercise, requiring software where all this is inputted. Okay, and by way of comparison, a passive house space heating demand needs to be under 15, and a conventional home to building regs of today is about 150. So 15 kilowatt hours per metre squared per year on space heating, and the primary energy demand of 60 kilowatt hours per metre squared per year. And so that is including all the energy uses of the building, so all your plug loads, your heating, your hot water, you know, your telly habit, whatever it is, all of that is included in that. So it requires you to have sort of low energy, very efficient electrical equipment as well. And then an air tightness of 0.6 air changes per hour. So that's the kind of criteria that we're working to when we're designing Passive House. So we're looking to have very low U values in our walls. That's a measure of the thermal efficiency. Guidance here around window areas, that kind of thing. So this is optimal, okay? So when it comes to designing a passive house, there aren't any design rules. There's no one saying, okay, you can only have 30% of your north elevation glazed. It doesn't work like that. You've got to design and make it fit. So you can have large glazing on your north elevation if you want to, that's fine, but it might be that you need to adjust things in another place to compensate. You've basically just got to hit those standards and prove you've hit those standards. It's not that you've got to sort of tick boxes all along the way. But all of this guidance here, if you start off designing with that in mind and you're looking at your site right from the start with all these things in mind, you're going to be able to reach Passive House standard much more easily and much more simply without too many complications and compromises along the way. And you might well exceed the Passive House standard. So when we're designing, we're thinking very much about these things. We're thinking about which way the building is facing. Where is the sun in this equation? Where is our enormous energy source? And how are we going to design in response to that? We're thinking about exposure, so that's the surface area of the building. How complex is it? How intricate is it? How do we deal with that? Windows design is a big thing. And then thinking about our thermal, the design of our walls, the construction detailing of our walls. Designing for air tightness, and again, the simpler the building form, the much easier it is to achieve that. And then we're thinking about our natural ventilation and our mechanical ventilation. So, for example, the top photo there, that's going to have a very, very high form factor because it's got an enormous amount of surface area. And when I'm talking about this with my students, I get them to calculate form factor in their buildings and in other buildings. And it really is just about deciding what's thermal envelope, so which bits of the building are heated. So in this block of flats, for example, that central core there with the bins in it and things, that's not heated area, that's not within the thermal envelope. How much of surface area is there? That's, so if you've got undercrofts and bits cut in and bits come out, that's all including adding to your surface area. And then what's your total floor area, ignoring the internal partitions and the external walls. And you can quite easily from that work out what your form factor is. So I'm telling my students, aim for 2. Try and have that in mind. You can test your design as you're going along. When you're getting too many bits stuck on it, just have a little moment of reflection. Think, is this low energy design? Without killing your passion, if possible. So an orientation that is predominantly north-south is easiest for Passive House as well. It's not the only way to design, and not all sites permit this to happen. But if it is possible, it makes it easier to achieve the standard. And that's because you can take maximum advantage of the south-facing glazing and the sun, and you minimise the difficulties of overheating that come with a west-facing elevation. So there's 2 advantages there. You need to think about how close buildings are to each other, obviously. And yeah, just more on that sort of sun angle thing. So you know, in the summer when the sun angle is really high in the sky, it's easier to provide shading so that you can keep the sun off the glazing. In the summer, ideally, you want to be keeping the sun off the glazing. In the winter, when the sun is lower, you want that sun to be coming right into the building as deep as possible. So that's the kind of optimum. And it may be that your home doesn't overheat at the moment. It may be that in 20, 30 years' time, you're retrofitting some glazing, some louvers or some blinds or something, which is a relatively easy thing to do in the future. So you don't necessarily need to have that at the moment. It all depends. So there we are. There's the summer and winter sun coming in. This is actually my house, this photo here. So we live in a passive house, uncertified, but it works very well in that we do get our sun in the summer, in the winter, and not in the summer pretty much, because we're fortunate enough to have that south-facing aspect. It's more complex on the east and west elevations because the west sun, in particular the sun from the west, is low all the time and still quite intense. So in the summer, it can get quite hot in buildings that have a west aspect. And the shading is more complex. So you've either got to just block out your daylight, or you need to have possibly some vertical louvered blinds so that you can angle them to prevent that very low west sun coming in. Just a little bit more technical to achieve. So that's Hannam Hall in Bristol that's gone for these kind of louvered facades. You see that quite often in Passive House, where the whole facade is kind of extruded off the building, perhaps with a balcony or something, and then the shading can be managed quite effectively. And it can also form a medium for growing plants up. And vegetative cooling is a really big thing. You know, some of the leaves provide coolth because they absorb that heat and the moisture out of the air, and they also provide more shading. So there's sort of lots of opportunities that can be garnered from that way. And then, you know, optimal passive house design, you might be looking at your window proportions. This doesn't always work out, but as a general rule, you're looking to have more windows on the south if you can, less on the north. Horizontal windows work well, because they allow in as much daylight as you're going to get, but reduce passive solar gains and minimise the amount of heat loss through windows. So horizontal windows are the optimum for window design with Passive House. Okay, then we look at trying to get our fabric as efficient as possible. So every aspect, floor, window, walls, is insulated as much as possible. This generally means that Passive House homes have a really quite chunky walls and roofs because they've got a lot of insulation in them. They can be much skinnier, but then you're having to use insulation products that aren't necessarily as friendly to the environment, high-performing ones, and much more expensive. So you do see some nice, really large, chunky walls on Passive House properties. Okay, so that goes without saying, you are putting on lots of insulation. Just a little note on balconies and walkways. So, you know, if you're having lots of them, then they are cutting back into the building, increasing the surface area, increasing the junctions. So balcony number 1 that's sticking off from the front is much more preferable in Passive House to balcony number 2, which is recessed back into the building. And so you'll find, like in that bottom photo there, kind of deck access works quite well for Passive House because you've got the benefit of the decks providing shading to the windows below, and then people can walk along, and there's no interruption in the thermal line. You've still got this sort of very simple thermal line going along here. It's not dipping in and out. So that works quite well. And Jim's told me this is just going to look silly to everyone, but I'm going to put it up anyway. He's like, just take that off, Louise. But I've left it in. So this is a wall here. This is inside the house. This is outside the house. And this is the same thing, wall, inside the house, outside the house. This is just showing how, you know, if you're attaching a balcony, you've got to attach it back to the structure, and structure is usually something that may well conduct heat. So you need to do quite clever things about preventing heat from travelling from inside the building into that bit of structure there. So this one is working really well, but quite typically balconies are put on and you end up with lots of heat being lost down this structural element. So something to consider. And of course, if you are having recessed bits of your building, you've got to insulate all the way around them. So it does get quite complex. You see there's like quite complex detailing here with a reduced ceiling, which doesn't run through structurally here. And you've got to insulate the floor. So simplicity does make life easier with Passivhaus, to a point. And then, of course, the air tightness. So this is preventing air leakage, any unregulated infiltration, removing that from the equation. So this is an air tightness test going on here where the house is being blown up and then the pressure is tested and then it's timed to see how long it takes to reduce to a normal pressure. And then it's reversed by sucking all the air out and doing it the other way around. It's quite exciting when this is all going on. So why do we do this? We do this to prevent unnecessary heat loss in the building. However, it doesn't mean that your air is really stale or and you lack humidity. In fact, the air quality in passive houses is really, really good because you've got your mechanical ventilation going on. So your mechanical ventilation is running all the time. It's running by this unit, which is about the size of a washing machine for a typical house. And it's taking fresh air in from outside and it's pumping the fresh air around to all the rooms at a reasonable rate of air changes that are appropriate. And then all the wet rooms, like your bathrooms and your kitchens, they have extracts coming from them. So all the stale, moist air from those smellier places is being taken out. So there's this continuous circuit of air. Now the clever bit is that the stale air, whilst it's being released, the heat that's in it, because it's warm air, is transferred into the fresh air. So your fresh air is being heated by your stale air and they cross over in your unit and then the stale air is expended. So it's very efficient. It's running, I've got this figure in my head, about £30 a year to run this thing. It's running on about sort of a very, very low pressure. So there's the, very low velocity fans. So it's very quiet. We can hear our extractor in our kitchen going, but only if the fridge is off, So in other words, we can't really hear it. So it's completely silent. In most of the rooms, certainly in all the supply rooms. So it's a fantastic piece of kit. It has filters in it, so we know that the air coming out is extremely clean because it's filtered, especially if you live in an urban environment. The air quality in the passive house can be really very, very good because all the pollution, the dampness is taking out, so drying clothes and that kind of thing is very easy in a passive house because all the moisture is continuously being extracted. So it does give you a very good quality air environment. So this runs all the time. In the summer, if your home starts to get too warm, then you need to ventilate it conventionally by opening your windows and allowing air to move across. So the same way that you would ventilate a normal house. Hopefully your architect will have designed it to be good at cross ventilation or good at stack ventilation so that air moves through it easily and you don't end up too hot in your home. So, that's the kind of processes for ventilation within the house. So your heating system you should need a much lower capacity heating system or no heating system. Typically though, you will have some heat input. So, you know, you'll have something there that's providing you some heat in the winter. But your reliance on it will be much, much lower. Okay. So you need space for your services, of course, and that's more important in a passive house because you have got more kit. So you design your passive house and it's built to those levels of fabric efficiency. And then to, you know, so you've taken a significant step towards zero carbon at this point. And then you perhaps add a heat pump, so a very low energy method for providing heat with your much lower demand. And then perhaps some PVs on the roof, or else you're using renewable energy from the grid to sort of finish off that equation. And then you can call yourself zero carbon. So I'm going to talk about this project today, and also just want to say hello to Liz and Mark, who are in the audience, because this is their house. And we've been working with them on this for a couple of years. And they have lots of sort of inside info, obviously, into what it's like to live there and how energy works for them. So if you've got any questions about the energy in their home and how that works, I know that they've been taking a keen interest in that. So they can be happy to answer any questions on that. But I'm just going to tell you a little bit about this project and how we've actually realised what I've been talking about in terms of these design aspirations. So this is Greenbanks. It's on the roads between North Nibley and Wootton, so not very far from here. It's an amazing site. So it was a cottage, an 18th century cottage of solid stone construction just outside the village, just underneath the monument. So you can see here in this photo, this is the cottage and there's the Tyndale monument there. So really spectacular views over the Severn Vale. So it was a small two-bed cottage with a couple of extensions on the back when they bought it. The extensions were very poor quality. The cottage was solid stone, but of not any particular sort of significance in terms of conservation or heritage. So we did a pretty thorough appraisal of the building, and there wasn't much of any value in there. The systems were pretty degraded. The windows were, you know, no good. The house didn't work very well in itself. Soundproofing was pretty bad. The light was very bad. The rear rooms were damp. The rear extension rooms were damp. So there were various kind of problems with it. Liz and Mark were very keen to have a sustainable brief for their project. So we talked about these things and came up with a kind of brief that we set ourselves for the project, which was about operational carbon, embodied carbon, and various other sort of features around water, biodiversity, that kind of thing. So that was the brief we were working to. I won't go into details, but there was lots of discussion about new build and retrofit. We sort of did a lot of analysis about this, whether to keep the actual cottage or not. We ended up keeping it, so that was one of our very much kind of build less. We managed to build less in that way. So, you know, thinking about pros and cons of it, we knew that we could get a better operational carbon load if we did demolish it and build entirely new, but you know, playing around with the carbon emission figures and that sort of thing showed us very much keeping that cottage was the better thing to do in terms of carbon. It was quite a complex decision, but in the end anyway we did decide to keep it, and it was really interesting to work with this existing building. So this was the kind of final design, if you like. So most of the house is behind the cottage, and this is to sort of minimise its impact from the road, to take advantage of the topography. The topography was very steep at this point, and to give them lots of opportunity to appreciate the fields to the rear, whilst also taking advantage of the views to the front. So here you can see the section. So the whole building originally the building came out about as far as here, the existing cottage. So we've actually ended up excavating quite a lot more into the hill and have quite a large amount down at subterranean level with windows out to the front, and then the whole of the top floor. So all of this bit is the new bit, and here's the old cottage. So the whole of the top floor is now the living spaces, and downstairs is the bedrooms and storage and bathrooms and that kind of thing. So the top floor appreciates the views out over the Severn Vale, and also the views out to their garden and the field behind, looking up to the Tyndale Monument. So it's a really spectacular site. So here you can see the lower ground floor. A lot of it is in the hill here. And there's a large storage area, some bathrooms and a couple of bedrooms in this back section, and a couple of bedrooms in the existing cottage here. And then upstairs, you can see that the whole of the cottage is now turned over to a really nice big living space here. There's a snug and a couple of offices, and then a large kitchen dining room. And so the whole of this top range here is also able to appreciate these incredible views out this way, as well as looking back up the other way. So that's the sort of arrangement that we've gone for with this building. And as you can see, it is now a large house, but we've tried to sort of minimise the sense of the new imposing on the old by putting in these walls here. So these are some stone walls, random rubble walls here on either side, which kind of shield the top range from the road, the main road, which is down here. So that was the kind of design solution. There are lots of features to the design solution, which I will sort of go through as we go on, that respond to the embodied carbon considerations. So retrofit being one of them, reusing things like the roof tiles. They were all taken off and reused as much as possible. We really tried to simplify the building footprint. So at one point we had less space downstairs because we didn't think we needed it, but actually it made it much simpler to keep these lines just consistent all the way through and not step it within the land. It would have just made it more complicated. So it was advantageous then to do that. So I'll just run through a few photos of it being built. So you can see we've got some excavation going on here. Now, there was a lot of concrete to do what we wanted to do, so that was one of our concessions. This is the base out the back, and we've got full tanking going up there. So the whole of that lower ground floor at the back, we have put a lot of concrete into the ground at that point. So holding my hands up to that. So here you can see it's come up to the full level. So it's level now at the back with the land going out the back. Here you can see we're putting in the joists. So we're trying to make some amends really here. So we're using posi joists. These are extremely lightweight. There's very low deflection on them. You can see there's very little to them. So they're using very little material. They're very easy for running services through. You can see there it's very easy to run services through. And we know that in this building we're going to have these ducts taking air to and from different rooms. So thinking about the integration of your services and designing for that is really important with Passivhaus. Otherwise you end up with all kinds of complications, boxings and trauma around that sort of thing. So being able to set things out to work really well in terms of your services and considering the whole thing holistically is really important, just to keep things simple. So with this structure, as I say, it's very lightweight. We've avoided steels, heavyweight steels. We've got some very small amounts of steel in those posi joists. Our spans are maximum 6 metres. So we're really avoiding any kind of heavyweight structural. This is the structure. There's nothing other than that going across from those 2 points. We also asked, and our structural engineer is very well educated about Passivhaus as well. So she was designing to 100% utilisation. So she's designed in her tolerances. But quite often structural engineer will chuck a bit more in just to be on the safe side. But it's not necessary to design. If you design well and confidently, to do that. So, you know, the whole industry is sort of, you know, gearing up to this and everything. So here you can see the timber frame going up. So the whole of the top floor was constructed from these timber I-joists here. They're about 300 millimetres deep. And again, that is the structure there. There's nothing else hidden within that. Sometimes they're doubled up if they need to be, but generally that is the way they are. They're about 600 mil centres, and they will be full-filled between them with blown cellulose insulation, so, you know, newspaper, basically. So each of those slots there will be filled up with newspaper. So it's a very simple construction. Because we've got this 300 mil depth there, plenty of insulation, really good U values. We're using recycled material, we're using a natural material, a timber-based material, so we're lowering our embodied energy by doing that as well. So we use it, there are a few bits of glulam in there. I think this photo possibly shows a bit of glulam in there. So we're using solid timber sections occasionally where we have a large span. So in this place we've got a big opening between the kitchen and the hallway, so we needed to have something a bit extra in that bit. So we have got some glulam in there occasionally around the top. So this is a detail here, and so by using these very slim I-joists as our wall construction, there's very little thermal bridging through that because they're very skinny. The actual ply fin in between there is only maybe 6, 7, 8 mil thick. So the actual passage of heat through that wall is very minimal. It's sort of been designed out as much as possible. So there the building is being covered in this blue membrane, a breather membrane going on all the way around the outside just to contain it. It's winter time now. So that's the inside of the cottage. Everything's come out because it was not in very good state. The floors were very wobbly, and so much remedial work would have had to go into it that we decided we'd sort of start from scratch. You can also see that we've put in some really nice oak trusses here. So, you know, very lovely. New roof going on as well that could be very well insulated. All the gypsum plaster has come off those walls and it's been stripped back to be rebuilt. And there you can see now the floor has gone in, the new floor has gone in, and we're starting to line out the ceiling there. So that's sort of getting rebuilt, if you like. This is inside the main bit at the top. So we've got this green here. So this is called smart ply. So the process of making your building airtight can be really complicated, but there are some really helpful materials out there, and this smart ply is one of them. So it's plywood, but it has this lining on it, which is airtight, basically. So we can use that really easily to line our walls. So that makes that pretty simple. You can see it going on there on the ceiling, and then it's going on the wall, just enclosing those cassettes. And then you can see there all the tape. So every time one of these smart ply sheets joins another one, it needs to be taped up because that's where the air is going to get through. So we're trying to eradicate all holes. We don't want any holes in this building at all. So everything is either an airtight material or it's taped together. So every airtight material will meet another one either by tape or membrane. So you can actually see here all these little blue sticky bits here. This is where the blown cellulose has been added to the wall. So they will have come and drilled a hole in the plywood, inserted their hose and fulfilled those cassettes with the blown cellulose insulation so that they can make sure that it's completely full. If it was a really big area, you might end up with little pockets and little gaps and things like that, which would not be advantageous. So by using this cassette system, you can be pretty confident that you've filled that cassette really well and that it's completely stuffed full of the stuff. And then they're going around and taping on top where the holes have been made just to seal that off again so it's airtight and that insulation is contained in there. And then we're battening out on that inside wall there. So yeah, you can see the tapes on all these edges here. Everything's being taped in back to the door frames to make sure it's all airtight. And then battening out on the inside so that you can run your wires through that. So all the big services will go in the floor, and then the wires, the electrics and smaller pipes can go in that service zone there. Okay, so a zinc roof. The main range, the new range, has got a zinc roof, which is a low embodied energy material. It's fully recyclable. So, you know, all our decisions are being informed by these processes, by these factors. And there it is, the old bit is catching up. That's being done as well. We had quite a lot of discussion about the external cladding. We thought about many different ideas. Here are some of them. We were certainly looking for some kind of mechanical fix material. So lots of people like brickwork. Well, I really like brickwork. But we were looking at these alternative terracotta tiles that actually just hang on. So they're fixed but very lightly, and they can hang on a wooden batten. So they're, you know, compared with a brick wall, which is stuck together, there's a lot more material in it, it's a lot thicker, it's a lot more transport, weight, all those kinds of things. This was a kind of less embodied energy option for brick. Slightly different look, but I thought it was really nice, quite expensive. Timber as well. This was a profile cement board. Mark and Liz didn't like that one. In the end, we went for slate. We went for reclaimed slate because we thought this will look fantastic. We can get it reasonably locally. When we look at the embodied carbon of slates, which we did in some detail, it was coming out top when we compared all our different materials in our kind of analysis of their embodied carbon. So that's what we did. So we have hung the slates on the side of the building. There they are going on. And we're really pleased with how they come out. I think it looks... You were... Yeah, there was a little bit of scepticism from Liz, but she had enough trust to go with it, and you like it now. Yeah, good. Yeah, so there it is going on. It was quite a relief to all of us that it looked so fantastic and that Liz liked it as well. So the timber we're using is Accoya, which is a timber which has been heat treated, or is it pickled? Pickled, a timber that's been pickled so that it is expected to live for at least 50 years. It's not edible anymore by anything. Nothing can eat it. So it's a very good timber to use, very durable, long-lasting timber that almost ceases to be timber through its treatment. But it doesn't need to have any surface treatment, which is another really good thing. You don't need to be doing maintenance on your buildings if you can avoid it. So, you know, by using a timber that doesn't need a surface treatment, that takes out another process, it takes out another opportunity for that timber to get degraded or whatever, or neglected. So, you know, that's another part of our consideration. What can we do that isn't going to have a maintenance burden to it? So what have we got going on here? So we're getting plasterboard up now. So the internal spaces are now being lined out. So this is a sort of palette of materials from the outside. We've got the slate with the Accoya timber. The windows are timber windows that are factory painted and factory finished. Then this is the Accoya cladding here. As you can see, it's very nice, light sort of fresh timber. And then we've got the Cotswold stone walling in there as well. And then the lime render. So the old building, we finished with insulation on the outside to improve its energy efficiency. We're trying to bring that old building with us, and it was because it was such a sort of simple form and solid stone. the detailing around that was not too complex. We could sort of bring that along with the new build so that in the end, so that you can get a passive house standard for retrofitted buildings as well, which is not as onerous as for new build. But in the end, we've managed to achieve the new build standard on the whole building because we could do quite a lot to the existing building to bring its thermal performance up and to air tighten it as well. So that's a picture inside the sitting room, excuse me, with that truss in place there. Haven't got that many interior photos, just a few more from the outside. And that's the entranceway, which is at the top level. So you come along and up some steps and into the building at that level. And that's the wall there. And yeah, there are the steps. And this is the magnolia tree that clung on to dear life throughout the whole build. And it was worth it. It's still alive and going well, despite the disruption around it and total chaos that it endured. So Mark very kindly had a bit of a look at their energy use for the 6 months between January and June of this year. So, you know, his comments were that the temperature inside has been very stable. They haven't had these big fluctuations that you get when the weather changes, because it takes a very long time for the temperature to change in the house because it's so well insulated. Saying it could vary by perhaps 1 degree during the day, so very stable. So they have used heating in the winter months, but find that they can have their heating on overnight, in the night when the electricity is cheap, and then because the building doesn't lose any heat, that heat just hangs around during the day, so they're able to just heat a bit at night to put the temperature up when it's very cold outside. You've got some underfloor heating in some spaces, haven't you, and radiators downstairs. Yeah. So because the hot water tank and all those things are very well insulated and they've got a home battery, pretty much all their electricity can come from their PVs or from a bit of night electricity. This is for their, not obviously for their, well, including their plug loads, because they've got a battery as well, so they can charge up their battery. So Mark's given us some figures here, and you know, there's fluctuations in the number of people living in the home. They've got 3 children. Some of them are there all the time, others are come and go sort of thing. So sometimes there are a lot more people there than other times. So the figures fluctuate over the time there. Also, there's been some sort of drying out and initial getting the system to bed in the initial months. And Mark's also has quite a lot of time for fiddling around with his different tanks and things, and that's ongoing. So he says here he's confident he might even be able to improve it from this. But that's where it is. So, you know, the target for Passivhaus was 60, and the house in the first 6 months is working at 42. Potential, you know, possibly a bit better, but we'll see. It was quite a mild winter, who knows? And also obviously quite a lot of winter heating is November, December time. So who knows? It'll be interesting to see how this unfolds. So absolutely well within the Passivhaus targets for primary energy use and heating demand as well. You know, this will become the standard. We just don't know when, but we're moving towards that now. But yeah, at the moment, you know, a house that was built a little while ago, and so not a brand new house now built to the modern standards, will be, you know, perhaps using 10 times as much in terms of space heating energy, even more. So, and with the battery technology and the, you know, the very efficient heating systems, the air source heat pumps and all that kind of thing, adding those technologies in and the PVs, then that sort of really brings it down massively in terms of getting towards net zero. Yeah, that's all I've got on my slides. So thank you.
Thank you.
Question is about social housing, council housing. How close are we to our council housing providers and housing associations adopting this? And yeah, okay. So you know, it's carrot and stick. So with housing with social housing, it's makes quite a lot of sense to build like this if you're thinking long term, because if you've got very low energy housing, your tenants are not going to be in fuel poverty, which is a real bonus to you as a landlord, that you've not got tenants who are so poverty stricken that they can't heat their homes, because then they're perhaps paying their rent more easily. Also, you've got less building problems around mould, damp, that kind of issue, because you have such a good air quality. So, and the sort of maintenance of it and the build quality of it. So there are quite a few housing associations who are sort of progressive ones who are thinking and doing and beginning to do this. It's carrot and stick. The incentives are that it makes sense. The stick is that they're going to have to soon anyway build to pretty much this standard, because that's where we're going. But I think that if you're building a house with the expertise from the beginning, and you are designing for this, and you're designing using all those principles that I'm talking about how you simplify, how you make it work as easily as possible, how you take the complications out of it, I don't see why it needs to be any more expensive than okay, so your window spec might be a little bit more, but we're moving towards needing to have those things for building regs anyway. So, you know, you're ahead of the curve a bit. Yes, I mean, my mum, when she comes to my house, she says, "Oh, it's terribly quiet," because it is very quiet in there. And you know, she's coming from my sisters with 2 young children making an enormous amount of noise. So that, yeah, but she comments on how quiet it is. So yeah, I understand it can feel a little bit different than if you're used to a home that's creaking and groaning and there's air moving around more, then it would feel different. Yeah, I mean, not many people kind of mind that, I guess. I mean, in your situation, perhaps you could have a fan on to sort of.
In the summer you want it. For the old cottage, did you retain the thermal mass of the existing walls?
Yes, we did. In fact, we exposed the thermal mass more. Previously, the walls were lined out with stud work. So we took that back and lime plastered them on the inside. So we're now utilising the thermal mass in those walls in most of the rooms.
So it's just the stone and the plaster?
On the inside, yes.
Oh, but you've done things to the outside?
On the outside, we've insulated and then lime rendered on top of the insulation. They were, what, 400 mil. Yeah. Yeah. So that the old house should be working better in terms of thermal mass. Yeah, we've lived in ours for 7 years and we've changed the filter on our MVHR too late, didn't we? So we had to replace we had to do, yeah. So 1 pump change in 7 years, which was avoidable if we'd been a bit more on it. So we should have changed the filters, every couple of years? And we missed it. It's most typically on the inner skin. It's most helpful if it's not, it can be as simple as the plaster. So the plaster acts as a air tightness layer. So if you've got like a solid wall and you're plastering it, that can be your air tightness layer. It's that simple. It's a little bit more complicated because if you're chasing out your back boxes and that kind of thing, then you've got to tape behind your socket boxes. So there's a bit of complication with that. Typically it's on the inner face. I guess it's just easier to kind of put it there. If you're using a membrane and it's right on the surface, that can be a bit problematic because you might put a picture up, or you might puncture that membrane in some way. So if we're using a system that has membranes in it, we'll try and put it, at least have a service void or something in between so that it doesn't get compromised. But it can form all kinds. It can be all kinds of different things. You know, in the floor, it can be the DPC can act as it. You just have to make sure it's taped onto the next thing when it gets to the edge. That's the critical thing. You sort of track it around the building. And then when you're doing the air tightness test, you go around with a little smoke blower and see where smoke kind of disappears or puffs out or stuff to kind of work out where it is, and then they'll scurry around and sort out that problem quickly. You can get decentralised systems as well that just work on a room basis. So you haven't got the investment of a system that's going over the whole house. You can get little ones that literally just deal with one room and provide ventilation, but don't lose the heat as well. And they're coming down in price quite significantly. They are, aren't they? Those things. Okay, so the certification is done by a Passivhaus certifier who is independent from the project, and they are paid a fee to check the design. So the design is done via this software called Passivhaus Planning Package. And then also the architect, the Passivhaus designer, needs to provide all the evidence that the build has been done to the right standard. So that process costs, you know, a few £1,000s to go through that process of getting the house certified. So that'd be an independent person who is brought in to do that role.
Yeah. So who is ultimately who issues the certificate? Is it a local authority or is it?
No, it'll be the Passivhaus Institute who issue it, who certify it.
What impact does the proactivity of the homeowner have on the passive house? Is it something that you can have built and just live in as you do normally, or do you need to, you know, things like keeping track of energy usage and even things like using the blinds in certain ways? To what extent do you need to be kind of proactive in your pursuit of the?
That's a good question. I'm just trying to think how to answer that one. I mean, I would say, I'll see what Jim thinks in a minute, but I would say, and possibly Mark, that you can live pretty unconsciously in your home. I mean, we do, don't we? Yeah. To be honest, we don't really think about it. The only thing we manage is our overheating, which everyone does, by opening windows and closing blinds. So we manage our overheating in that way.
I think we're gonna wrap it up there. Thank you so much, everybody. Massive thank you to Louise.